Hey everyone, my name is Bilal and in this video I'll introduce you to our machine learning project at NYU Shanghai. For our machine learning project, me and my partner Kenton decided to perform multi-class classification on colorectal tissue images obtained from patient scans. The underlying motivation for attempting this project was that colorectal carcinoma is one of the world's leading causes of cancer-related death as well as the world's most diagnosed cancer. In fact, according to recent epidemiological data, colorectal carcinoma has most significant burden in European countries and is still associated with high mortality rates. Therefore, the correct prediction of cancer as well as the early diagnosis is highly crucial for the well-being of the patient. However, given a scan of a colorectal tissue image, the traditional visual assessment is highly unreliable and also time-consuming due to the subjectivity of the evaluation. On the other hand, the automated analysis is also very challenging due to the variability of the architectural and the coloring characteristic of the histological images. Therefore, in this project, we propose a deep learning approach based on convolutional neural network to correctly classify these cancer images into one of the 8 classes.
Analyzing Patterns in Colorectal Histology by Bilal Munawar and Kenton Blacutt. Let's have a look at the challenge and the task overview together. We have a total of 8 classes of cancer tissues which we're trying to predict, therefore we're dealing with a multi-class classification problem over here. The texture images are 150 by 150 pixels in size and we have a total of 5000 data points. The name of the dataset is Colorectal Histology MNIST and it's a collection of colorectal tissue textures available online. We have a total of 5000 sample cancer textures as mentioned before and the data is split into the following 8 classes, namely tumor, stroma, complex, lympho, debris, mucosa, adipose or empty. Cancer images belonging to each of these 8 distinct classes are pasted on the top for a better visualization. All images are RGB, magnified by a factor of 20. The data is also anonymized for relevant purposes. Moving on to the pre-processing of data, we performed one hot encoding of our data labels, which was crucial for our implementation of the maximum likelihood function. This maximum likelihood function concerns with maximizing the probability that the data belongs to the correct cancer image. We split the data into test, train, and validation set consisting of 3200, 800, and 1000 data points respectively. Because we were dealing with a small number of data set, we performed data augmentation, which is a classic regularization technique. By performing small random transformations on test data, such as rotation, zoom, translation, sometimes increasing noise and luminosity as well, we were able to achieve a data set which was 75% larger than the original data set. Moving on to image normalization, we subtracted the mean of each image and scaled it to unit variance. This helped us improve the conversion speed. Let's visualize the data distribution per class after data augmentation. We could see that our data is very well distributed across the class, so we did not run into the problem of having an unbalanced data. Setting up the loss function. Each image belongs to one of the 8 classes. Target per sample is following one hot encoding scheme. Given an each image, the model predicts the correct cancer class, yielding a probability of yk for each class. Non-target classes for each sample yields a probability of y sub naught equals to 1, therefore these probabilities are not counted. Only the probability of true class yields a probability of y sub 1 equals to y sub k. By fitting our model to the dataset, we try to maximize the likelihood that our predictions match the correct labels. Therefore, we trained our CNN architecture from scratch, consisting of 2 convolution layers, each having a ReLU activation function and a maxpool layer. Let's visualize our base CNN architecture. Each layer consists of a convolutional layer followed by a maxpool layer. The last maxpool layer is fully connected to a fully connected layer which passes in the input to a softmax layer. The softmax layer outputs a vector consisting of 8 entries with each entry corresponding to the probability that the data point belonged to a certain class. Let's visualize the training and validation loss. We could see that our training and validation loss gradually decreased over time and we did not run into the problem of overfitting our data. Therefore, we did not have to try the early stopping regularization technique. Let's visualize the training and validation accuracy. We could see that after training our base CNN architecture from scratch, we were able to hit the accuracy of around 60 to 70%, with a test accuracy of 66%. However, we realized that training our base CNN architecture from scratch would not be a really good idea because we still did not have a large number of data points. Therefore, we tried to implement transfer learning, which Kenton will elaborate more on now.
In our case, transfer learning consists of taking models previously trained on the ImageNet dataset, unfreezing the last few layers, placing a softmax with 8 classes at the end, and plugging in our data to adapt the model's weights to colorectal tissue images. So initially we were attempting to use a VGG16 through TensorFlow and Keras, but the computation time was extremely long and the results were not good, with our accuracy rate barely exceeding 70%. So we moved on to ResNet models as recommended in a Kaggle competition, and immediately achieved much higher accuracy rates. In total, we performed transfer learning with ResNet 18, ResNet 31, and SqueezeNet. Initially, we were only modifying the weights of the last 8 layers, yielding results of around 94% accuracy. We then unfroze all the model's weights and reduced the learning rate progressively, yielding an accuracy rate of around 96%. Here you can see what a ResNet 18 architecture looks like. So when I say that we froze all the weights, what I mean is that all of the weights were frozen up until this last section. So ResNet 18 with frozen weights, after about 1,000 batches, we had 96% accuracy. Then, as you can see here, the training and validation loss initially were falling until about 800 batches before plateauing. Then when we unfroze the weights and progressively decreased the learning rate, you can see that it kind of sporadically changes, but it's only a change of about 0.5%. You can see that the training loss continues to fall, but the validation loss plateaus after about 800 batches. So what we may be doing here is overfitting our model to our dataset. SqueezeNet performed very similarly, achieving results of about 92.3% accuracy. And with unfrozen weights, once again, it kind of sporadically changes due to that learning rate changing. But overall, it improves slightly, going up to about 95% accuracy. Here you can see the confusion matrix of the ResNet 18 model. And here you can see that the most confused images for ResNet 18 were in fact the complex tissues. Complex tissues consist of more than one type of tissue being present in the image. Therefore, it's no surprise that the image was misclassified. Here you can see the heat map, and you can tell that the model is sort of taking one part of the image, one tissue, and using that one part of the image to classify the whole image as belonging to that tissue type. So here's a summary of the different performance for the different models. So to make our model accessible to people unfamiliar with machine learning and computer science, we created a user-friendly web interface. Since we were running our models on an Amazon SageMaker Jupyter notebook, we pickled our model, then used the SageMaker API to upload our model to an S3 bucket, and then downloaded the model locally. We then created a Python server with Starlet and loaded the PyTorch model onto the server with the FastAI module, returning the top 3 classes along with their probabilities. This was uploaded along with a JavaScript/HTML frontend to a server called Render. And this is the URL in case you're interested in looking at our front end. As mentioned earlier, the images included in this dataset are 150 by 150 pixels, but in the real world, histological images are usually 5,000 by 5,000 pixels each, and they contain multiple tissue types. So if we had more time, we would have changed our API in order to process these larger images by breaking the images into chunks of 150 by 150 pixels, and then allowing people to pick the categories they want to be alerted of, and after the image is processed, see a heat map of the image with the interested areas highlighted. For instance, mark tumor as the interested category, upload the image, and then see a highlight of the areas of the image where a tumor was detected. This is sort of how the concept would look in real life. And for key references, in case you're interested in learning more about this project, you can visit these different links. They were very useful for us in order to sort of get started and get an idea of how to deal with our data set. Thanks for listening. Now I'm just going to very briefly introduce our API. First, you visit coloncancerdetection.onrender.com. Then you pick an image. After clicking Analyze, you get the top 3 classes with their respective probabilities. Perhaps one day models like this will be used across the world to help with the early diagnosis of dangerous diseases. If interested in contributing, please check out the project and the GitHub link listed in the video description. I hope you enjoyed watching our presentation almost as much as we enjoyed creating it. Thank you.